All right, this is the functional test for the VSD PID fan made by me, Kaye. As you can see here from the get-go, we've got a custom-made hexagonal mesh, and we have the temperature sensor on top. There we have on-off switch, LCD screen for RPM, ambient temp, and desired temperature display. Then we have the temperature increment and decrement buttons, which will allow you to change the desired temperature. Around the back, we've got the back grill to prevent foreign objects from entering the fan. And then we have the 12 volt DC adapter, which is plugged in. That 12 volt DC gets down regulated to 5 volts for the ESP32 on the PCB, which is enclosed inside. I will turn this on and it'll be set at something like 84 degrees, the desired temp, and right now it's about 80 degrees in this room. So as was detailed in the report, in accordance with VSD themes, the fan will never stop unless you turn it off. It will run at a very low RPM anytime the desired temperature is at or above the ambient temperature. And this is to avoid the high cost of startups. And then from there, anytime there is a temperature differential where you have the desired temperature below the ambient temperature, there is a linear differential algorithm that is applied that will increase the RPM. And then from there, a PID algorithm was applied to the RPM to ensure best control practices. So we will turn this on. Immediately you see the screen come on, you see the fan come on. The screen's a little bit hard to see. So we can see here we have RPM. It's catching up here a little bit. So we've got set temp 84, so it should be the lowest setting. As you can see, it's a very low RPM. And then we will now decrease the desired temperature. So you can see the RPMs increasing. You can probably hear the fan increasing in speed. And then the max RPM occurs about 20 degrees below the ambient. So right about there, you can see the rating for the fan is around 5,000. So it's roughly right in that range. And then now we will increase the desired temperature, and you can see the RPM is decreasing all the way back to where it was anytime you set it at or above the ambient temperature. We can also see that when I put my thumb on the scale here for the sensor, the ambient temperature increases. And you can see that the RPM has increased in kind. And just to hammer that home even more, we have a handy dandy blow dryer here. And you can see there we can see the ambient temp increased very high and the RPM increased to the max. And then now it is decreasing again. So that is the functional test with the enclosure interface, and next we will see the app integration. All right, for the app integration, using the Blynk app for iOS and Android, if we'd like to control our fan via our phone or a desktop, we could use this app. So via the phone, I'll navigate to the app. It says it's online. And here we have the RPM being displayed along with the ambient temperature and a slider for choosing the set temperature. And we also have an on-off feature. So this obviously doesn't turn off the power. That is an analog switch. This just turns the RPM down to 0 should the user want that to happen, and then obviously turns back to where it was when they don't. So currently we have 78 degrees, we're at 84. We'll try and set it lower. So now it's 67, you see the RPM increase. You can probably hear the fan going a little bit louder. And we'll go down to its something very low, maximum, so there we are again, hovering around the max RPM value for the fan. And then go back up. Decreasing. And then we will test out our on-off feature. So hitting off, you can see the RPM reduce. Probably hear the fan turn off. It'll go all the way down to 0. There you see the fan is turned off, and then we can actually just turn it right back on should we want to. Excellent. Then again, I will turn up the ambient temperature just by holding it. So you can see the orange there. The temperature is increasing, and the RPM is increasing. And that is the fan control via the Blynk app. All right, and this is the PID tuning demonstration video of the fan project. We can see here that I have the fan, and it is connected to my laptop, running Arduino firmware, and that is then going into a MATLAB script, which will plot the serial inputs with respect to the desired temperature, and then here I have a PID tuning log that I've been keeping track of all my notes. And so we will go over the firmware real quick. Alright, this is the firmware for the PID tuning. The firmware is basically the same as normal operating code. However, there are a couple things added just for the testing in particular. So you can see here that there are 3 types of tests. The first will just be a mid-power test, which can showcase the effect of the PID constants here. And then there will be a low to high power test, which will run it from the lowest RPM to the highest RPM. And then we can see the effect of the coefficients there. And then there will just be a 3-minute minimum or mid power test that will showcase the longevity of the effect of the constants. You can see here that I have hard-coded the ambient temperature to be 80 degrees and then included this if statement for the PID testing, which will make it so every 20 seconds the desired temp will fluctuate as necessary for each particular test. Here we have the MATLAB script, which essentially just reads in the serial data from the ESP32 and displays it in a plot, which you will see momentarily. This is trial 1, where I set all the constant values to 0. This demonstrates a baseline behavior without any PID control. We will run this MATLAB script, and then here you can see the plot where we have the motor RPM versus time, and then we have desired temperature versus time. This is included so that you can see how the RPM changes when the commanded RPM changes. And here we have at 20 seconds, the desired temp changes to about a medium differential from the ambient temp, and we have no change in the RPM. And this is again because all the constants are set to 0, and this establishes a starting point for tuning and shows how the system responds without it. So the first step in my tuning process was to define the appropriate value for the proportional gain, and this was trial 3, where I set it to 100 and the other coefficients are set to 0. And here we have 20 seconds, increase up to a maximum RPM value of just over 5,000. Keep in mind this is supposed to be at medium power, so this should be roughly 4,000. So what we see are the effects of a high proportional gain, which forces the system to react strongly to any error. And this illustrates the effect of having an excessively high proportional gain, causing the system to overshoot and reach a maximum output. And this was trial 6 of my testing. Here I was able to fine-tune the proportional gain down to an appropriate value of 7.5. Again, the other constants are set to 0. Here again, around 20 seconds, we have our increase, and this gets us to a more appropriate value of around 4,000 RPM. And you can see it's relatively stable and smooth. We're just having proportional gain, and this indicates a well-tuned proportional gain value. And with that properly set, we can move on to the derivative gain. All right, and after a few trials of adjusting the KD value, they were sort of inconclusive. So this was trial 9, where I had KP set to 7.5, KI set to 0, and KD set to 500. So I set it at a very high value. Here we can see it changing. Gets up to the 4,000 RPM. And as you can see, it just looks relatively similar to the proportional gain only trials. And this leads me to believe that the KD has a relatively limited role in affecting my system, and this validates the decision to minimize it. These findings actually corroborate the findings referenced in my report by Keith Curtis of Microchip Technology, where his team also determined that the derivative gain had little to no effect on full wire fan response, and that this is likely due to the unidirectional drive of the PWM, which can increase the speed. However, slowing is due to inertia and the load of the fan. So the derivative term has very little means of acting on slowing the fan. I did keep monitoring this, but moved on to the integral gain while setting KD to a low value. Okay, so after a few more trials, I just decided to keep the KD value at 0.1 to avoid any issues with the algorithm, setting it to a 0 value. So this was trial 13, where I increased the integral gain to 10. And here we can see it goes to the maximum RPM value. Looks kind of smooth and stays there for around 40 seconds. It's supposed to drop in accordance with the desired temperature change. However, it just stays at the maximum value. This trial is included to illustrate the negative effects of setting the integral gain too high. And it demonstrates the importance of careful tuning of the integral constant, because this can have excessive integration of the error, resulting in an overcompensation and really no change that is expected or supposed to happen. As you can see, it's still just it's going to stay at maximum RPM. All right, and after a few more trials, I got to trial 15, where I reduced the Ki coefficient to 1. And so it is a much lower value than 10. However, as we will see, the RPM will increase. And it initially gets to about mid-level, about 4,000. But as you can see, it's increasing over time. It's for this full duration at the medium power, and then it will drop. And it actually doesn't fully reach the low value again. So it's not getting to its full low value. And this shows that while the lower Ki value provided a better response compared to the previous trials, it did reduce overshoot apparently, and oscillations apparently. However, the RPM still increased over time due to the Ki value integrating the error over time. And this shows that while reducing that Ki value, it can help stabilize the system momentarily, but it's essential to achieve the correct balance to maintain a consistent RPM without unwanted increases. As you can see, this will just continue to escalate over time. Okay, and here we have trial 21, where we have still the KP set to 7.5 and Ki was reduced to 0.05. And here we can see that the response goes up to the applicable level of 4,000 RPM, and it stays relatively stable there. And this trial involved fine-tuning the Ki value to this stable level, and it resulted in the consistent RPM value without overshoot or gradual increase over time. As you can see here, it dropped back down to the low level. This same Ki value was tested in the previous trial with KD set to 0.01, and despite increasing it to 2 this time, there was no noticeable change in the system behavior. This further corroborates findings previously that KD has very little impact on our fan system. And this trial shows that a Ki value of 0.05 is acceptable level for stability, and we can move on to the min-max RPM testing phase. And this is trial 26. So this was one of the min to max RPM tests. The values used here were KP 7.5, Ki 0.05, and KD 0.01. These values were all good for the medium power testing. So here we can indeed see that the RPM increases in a relatively stable manner to the maximum value. Decreases, and it actually looks like that it doesn't quite reach the full low value. It's pretty close, so we will see how this changes over time. And yes, so we can confirm that the Ki coefficient value is a little too high. As we can see, it is not fully reaching the low value. So this indicates that while the response is generally stable, the integral term may still be accumulating errors slowly and leading to this gradual increase. So this highlights the change in behavior of the system under maximum load conditions and demonstrates the need for further fine-tuning at higher gains. Okay, and the final trial, trial 27 for the min-max RPM testing. We have KP at 7.5, KI reduced to 0.03, and KD at 0.01. Here we can see that the RPM increases. Relatively no overshoot and flat response at the maximum RPM. Relatively stable, all things considered, and then back down to the low RPM. And so this adjusted KI value to 0.03 corrects the gradual increase observed in the previous trial, and this achieves stability even at maximum load. So this trial demonstrates the final successful tuned PID system for this fan, highlights the effectiveness of the iterative tuning process, validates the chosen PI values. In summary, there is a dominance of KP at 7.5, the proportional gain, and that is essential for achieving stability and responsiveness. The integral gain, small values, reduce steady-state error, and fine-tune the system without causing instability, but it does have a limited effect, and the differential gain has a negligible impact, possibly no impact. There was a minimal effect observed, but I've kept the KD value at 0.01 in case the algorithm has issues with a zero value. And finally, we have our trial 28, which was simply the 3-minute medium power test. So already we can see that the fan RPM is roughly in that 4,000 RPM range. And we will monitor this for 3 minutes to ensure there are no major fluctuations in the output and that it does not increase over time, as we have seen in some of the previous tuning trials. Okay, and that is about the 3-minute mark. As we could see, the 3-minute test at medium power levels ensures the stability over the system over a longer period of time. During the test, some fluctuation was observed, approximately plus or minus 300 RPM in certain cases. This level of fluctuation is acceptable considering the tolerances within the Hall effect sensor in the fan and the rotational inertia of the fan, along with the analog nature of the system in general. This trial confirms that the system maintains stability and does not exhibit significant increases or instability over extended periods, validating the effectiveness of the final PID tuning values.